Our next presenter is a software engineer in the Chief Architect's office at Cisco Systems, where he is working on network virtualization and orchestration technologies. His technical interests include network engineering, configuration automation, system architecture, and data visualization. To tell us about working with large-scale networks in Python, please welcome Simon Knight.
Cool, thank you. So this is continuing some work that I started as a PhD student at the University of Adelaide, and yeah, it's a Python open source project, and continuing on at Cisco, continuing the open source side of it. So what we've been looking at is basically router configuration. So routers are, most people probably seen them before, essentially just a computer with lots of network cards in, and we represent them by this symbol, plug them into each other, and then they run routing protocols that then talk to each other and find the path, and then you build them into a big network, and you essentially have the internet. And by grouping these routers with different properties, such as an autonomous system, we can form different configurations. So here we could have two networks talking to each other. The essential thing is that the protocols and configuration running inside one network is slightly different to inside a different company's network. And then the protocols between them need to incorporate, or the configuration of the protocols between them needs to include information such as business relationships. So it's just a lot of complexity once we start building them into bigger networks. So this is slightly bigger network, but still extremely small in terms of the scale of the internet, which is like 40, 50,000 router kind of deal with plenty of networks. So what we're looking at is the configuration of these devices. And basically, each of these is configured, if they're configured directly, is in a low-level vendor-specific syntax, which is essentially fairly similar between each device, but slightly different. And that gets really tedious and error-prone, and and just takes time-consuming to do and to repeat that across lots of networks with slightly different properties. So if a router's only talking to other routers inside the same network, that's slightly different to if it's talking to routers in a different network, and getting all those properties right is important for the performance or for the network to actually work. So each of these, is very similar, but just slightly different, which is essentially really time-consuming and tedious and boring, and really doesn't scale when we get to big networks. So in terms of trying to do the configuration, one approach is to have like a database and push that into templates. And the problem then becomes, how do we specify these properties in the database? Because we've raised the abstraction then from typing it into each device individually. We can put the properties in the database, push them into templates, and push them out to the network. But we still have the problem of making sure the properties talking about this router is the correct ones and this one here, and getting the device level properties correct across the network-wide context is the challenging bit, and that's what we've been looking at. So we took a step back and trying to look at how someone would ideally design a network. So an extremely simple network here, for instance, you start on a whiteboard and draw up your routers, which are the circles here, and then draw something like the circles around them to have some sort of attribute like the AS, and then you might use different colors or different tags to start describing how it goes from there. It's pretty hard to capture from a whiteboard. I guess you could do some image processing, but we didn't. So the next thing that's slightly more computable is drawing in something like Visio. So we use YED, which is a freeware, it's actually a Java program, but freeware multi-platform program that you can draw diagrams in. We've sort of used it to draw networks, which are essentially a graph. And one of the key things here is that we have the attributes up here. So what we can do is, instead of drawing with a different color or a different label on the whiteboard, drawing the attributes. So where I had the squiggle cloud around a group of routers to represent an autonomous system, such as belonging to Telstra or ARNet or Internet or a different company, we can put these attributes on the nodes here. So for instance, we have this one's set as a router and the ASN is 2. So for a different group, it might be an ASN of 1. And I'll show those in a few slides. And then we can add some other properties like a route reflector to designate its role in a network and some other things which I'll get to. The problem is, though, that we could capture and draw it at a high level, but if that's just a GUI that we present to the end user, every network is slightly different in terms of how they want to configure their protocols or the links they're using, whether they're optimizing to be low latency or low cost. So trying to capture all these different requirements, we can't just draw your network, add some attributes, and then we'll build it for you, because it's not really going to work. So this is where the Python comes in. So one of the nice things with YED is that Visio and OmniGraffle don't do is that it can export natively to a graph interchange format. So it describes this network here that we draw up as a list of nodes and edges in the classic computer science graph sense, and the attributes on them, which means that we can use something, and NetworkX is a really nice Python package for graph manipulation and analysis, which can read natively GraphML. So we can draw up our network in YED, and I wasn't meant to use that again, and import it directly into NetworkX and start to do some things. So we can then iterate over the nodes, just native standard Python iteration, and get the attributes there, so we can see the nodes and then these attributes that were set, so the X and Y, the ASN value, which are set before, and then the other things like the route reflector, which might be a Boolean that we can do some stuff with. And yeah, so that's the attributes, which suggests that we could draw it up and then do some Python type operations to start building up these configs. We also can do similar things for the edges. So for instance, the edge between N12 and N11 could have something like a speed property that we could then use to do some analysis or run shortest path and do some standard graph operations. So the graph operations themselves aren't particularly groundbreaking, but being able to draw the network and then do these operations in a network context becomes quite powerful. And then we can start using other Python things like the list comprehensions really work quite well when we're talking about lists of nodes and edges. So here we could just grab the nodes that we've tagged in the graph with ASN attributes set to 1, or doing things like the edges between two ASNs, so that might be the link between Telstra and ARNet that we might want to treat differently. We can easily get them in the list comprehension, just looking where all the edges where the ASN of the source node is not the same as the ASN of the destination node. And we could, of course, with list comprehensions, build these up to quite powerful and quite complicated queries in a way, or apply like a function to the edges to filter, and that becomes really quite powerful. So the extensions, and this is really where our project comes in, is AutoNetkit, which has been building on top of the NetworkX graphs that I just showed. But the thing with networks is that we don't just have one protocol. There might be one that we run with inside the network, and then there might be different ones between the network, different networks, and then a whole heap of network engineering terms here. But whether we want to run within or between IPv4, IPv6, and different variants of all the different protocols. So essentially, networks are the way that we've been representing them here is as multi-layer graphs. So NetworkX is really nice to be able to represent a network as a graph, but we want to be representing each of the protocol configurations. So what we've essentially done is built basically a dictionary and wrapped it around in our abstract network model class, which has a series of dictionaries that the user can define, and then a heap of operations to make it fairly easy to work with. So we've done a bit of stuff with the magic methods to make this easy to use externally. So we can get things like the A&M. We can then access the different graphs in there. So for instance, the physical graph, which we're just referring to as phi here, we can then access node 1. I'm just going to quickly skip through all the details of this. But what we've done is by using the set attribute and get attribute magic methods, you can then, instead of having to access the node back through the graph like in the previous syntax, we just wrap around it, and you can then just set an attribute directly, like the test attribute, and then print it out. And then that's all set on the underlying NetworkX graph. So if I look back at the graph like before on the bottom line here, that's showing that the dictionary, and we can see that attribute's been set. And then using get items, so what we can do is by looking up that node in a different graph, because they're all referenced by ID, we can use get item to then go for this node N in the input graph and then get that corresponding property. So this makes it quite powerful when we're trying to configure lots of protocols at lots of different graphs. And then iteration, of course, is really quite handy to have with list comprehension, so we can then iterate over the graphs and print out their labels. So in terms of using AutoNetkit very briefly, importing it is fairly similar to with NetworkX. You load up the graph from we do a bit of initialization to set some default values, and then the basic API usage is essentially list comprehensions with just the set attribute and get attribute wrappers around them, so we can do things like printing the nodes again like we had before if the ASN is 1, and printing the edges if the source is not the same as the destination ASN. So fairly similar to before, but a little bit more succinct and a little bit more readable. Perhaps at a loss of a little bit of performance, but when we're building large network design descriptions, the clarity becomes quite nice. The thing though is that once we start dealing with lots of sequences of nodes and edges, it becomes quite difficult to see the context. So for instance, with the physical graph here, if we're taking that topology I drew before and we're creating a new graph, the physical graph, and we're adding the nodes and edges from before, if we then print out a list, we can do the Python list comprehensions is quite nice, but even for a fairly small graph like I drew before, it starts to get really hard to see, is this actually what I intended? So we can get the node list, which is a whole heap of nodes, and we get the edge list, which is an even bigger list of edges, and trying to see, is that actually what I want it to look like? It's quite hard to get the context here, and it's quite easy to miss one. And when you're building up multi-queries with different attributes, it becomes quite difficult. So what we did is built a visualization system, which actually isn't in Python here. We built that on top of D3, which makes it quite easy to palm off the GUI work to a web browser. And D3 works really nicely in tandem with Python. So for the visualization, we have the AutoNetkit main script, and that just posts as a JSON to a Tornado web server. So we just use Tornado. That works quite cleanly with our WebSockets for dynamic updating. So we get the script, and just like before, if we've created it with the input and physical graphs, added some nodes, changed the attribute like test and things like that, we can just call AutoNetkit update, and that will just look for Tornado running on the local host and send it the ANM. So just that network model wrapping the NetworkX graphs as a just JSON format, which is again quite nice and readable. Sends it across to the web server. That will then receive it and then send that across to the listening web browsers, and that's in multi-platform and works quite nicely. And there's a lot of really nice things you can do with D3 that I'm not going to get into here, but it's awesome. So in terms of doing some basic network graph creation using the API, OSPF's one protocol that runs within an autonomous system. So basically what we've done here is just taken the nodes from the input graph, so just all the routers in the network, and then adding the edges from the input graph if the source is the same as the edge, so just like the examples I had before. So all we've really done is just drop the links between the networks. eBGP is a protocol that runs between autonomous systems, so it's pretty much the inverse of what I just showed. We're just adding edges if the source is not the same as the destination. And iBGP is what's used within a network to talk about the external networks that you can see. So the very simple example is just creating a full mesh, which becomes quite nice as a list comprehension or generator expression here, and just iterating over all the nodes and edges in the network if the source is the same as the destination. You can probably write that more efficiently, but it shows that you can quite quickly create graphs based on these attributes. The thing is that iBGP running as a full mesh is going to be order n squared, so it doesn't work so nicely if you have a really big network. So what's common is people might specify something like a route reflector, which basically says rather than everyone connecting to everyone, connect to one central router or two central routers and build from there. And so in terms of expressing that with the syntax here, it becomes quite simple in graph operations. So if you remember right back when I was showing YED, we could set that Boolean attribute to say, is this a route reflector or not? If we go back to wrapping around NetworkX, we can just look at the nodes in the graph that we added before, group them by ASN, so that will just give us a list of all the, or a dictionary keyed by the ASN property, and then the nodes that have that ASN, so we'll get one and get a few routers, two, get another set of routers, and ASN 3, get the other set of routers, and then we can do some looking at that. So if I just grab the routers with a list comprehension, looking if that, just the list of all the nodes in that ASN dictionary if they have route reflector set, and then we can just do a basic check if there's a length, so if there's anything in there. And then we can do set operations on the sequences to see which ones have actually got it set, which ones don't. And then just basically create an edge between those that are the route reflectors and those that aren't, and add those edges. So we've just gone from having the full mesh there to doing this here. So the technical details aren't as important, but trying to show you that we can quite quickly create these high-level design rules by just a few lines of Python code. And then we can just do the other case. So if they don't have that attribute set, just create the full mesh as before. And that's that. So in terms of how that works, we just take, that was the input from Yed as GraphML, the loader which sets the defaults into an input graph, and then building up these overlay graphs from there. The whole purpose of this isn't just to create the overlays, it's to create the device configurations. So we've got another module, the compiler, which looks at each of those overlay graphs and then concatenates them down, or condenses them down to a device level model, because the network is configured device by device, but working at the abstract network model level lets you design it as a network. But of course, we still need to push these things out to devices, so that's what the compiler does, which is really just iterating over with just objects, inheriting from like a device or router and using functions based on there, and building up. Basically, this is what it looks like, the end product. So this is just rendered as JSON, or as dictionaries, and we can see that we've got things here that might be coming from IBGP graphs or the eBGP graphs, and OSPF down the bottom. So we've got a vendor-specific format here. It's not obviously in the Cisco iOS or Quagga formats that I showed in the earlier configs, but it's one level up from there. So what we can do with these attributes is push them out through something like SNMP or netconf or some of the programming APIs, possibly through to some of the more DevOps configuration for server systems. So a lot of the time that these networks aren't just routers in isolation, we might have a DNS server connected in which needs to know about the other DNS servers, or there's an interrelationship between the routers and the devices connected to them, the servers, and they need to know about the IP addresses, or there might be a DNS hierarchy that those representations where it's not just a device in isolation works quite well with this approach. And I'm particularly interested in the salt stack side of things, because seeing the earlier talk on salt stack, that this level of attributes could push quite nicely into some of the YAML configs for salt stack, and then to go from there provisioning it. But our work to date has been in configuring the device templates, or configuring the devices based on templates, so outputting those text files. So we've been using Mako templates, and as part of the compilation step, which is buried right down the bottom there, you can specify in the compiler which template you want to use. So this approach means that you can quickly configure for one type of device, whether it's a Cisco one or whether it's for Quagga or a different routing vendor. You can easily use the same design approach and then push them out, rather than having to rewrite all of your configuration for each different device that you're configuring. So we use Mako, which is similar to a lot of the other templating languages, and basically define your template. All we've really got in the template is iteration, conditionals, and variable substitution, because I've seen a lot of other configuration systems that bury a lot of deep network logic into the templates, and they become both hard to use and maintain, but also less portable if you want to change the syntax to a different vendor. It's very tightly coupled between the device configuration syntax and your network level design. So Mako works quite nicely, and you just define your template and then calling Mako with the node here. And you can then, using the get attribute and set attribute magic methods, it becomes quite succinct then to do things like the host name is just node.hostname, and that will grab that property. So trying to keep the templates as readable as possible, and you'll get the output such as down the bottom. Or for something like BGP, it might have a slightly different template, again applying just the node to it, and you'll get the output there. And then that scales across as many devices as you need. So that's generating device configurations. We've been playing around with emulated networks to test them out, because just generating the configurations isn't necessarily enough to verify they work, and to learn how to design these configuration systems. So the idea of emulated networks is just to, instead of buying hardware routers, which especially when we're at university gets quite prohibitive in expenses, you take the operating system that would be running on a router and running them inside a virtual machine. So we're originally using Netkit, which was running user mode Linux, and you just run the Quagga routing daemon inside that, which was really efficient. You could, with Quagga inside UML, you could run a router that would perform all the general routing functions in about 32 megabytes of RAM, which was very efficient on any sort of commodity device to build big networks. And then my work at Cisco has been on Viral, which is a virtual internet routing lab, which is a similar kind of idea, except it's running, of course, Cisco's iOS, and we're doing that inside OpenStack, so that's something that's coming soon. But the same general idea is that once we've generated these configurations, we can then push them out to these emulated networks. We could also push them to a hardware network. It's a lot easier with an emulated network, and then do some experimentation with that. So AutoNetkit, we extended it on to push the configurations out. So we've been using either pexpect or xscript, which is some nice as nice as expect can be, scripting libraries to basically just running the standard Netkit commands to archive the folder, transfer it over to the Linux host, unarchive it, shut down previous labs, and then start up the new one and verify that it's working. So that comes through like that. And the end result is we end up with just a normal routing terminal. So we can see, for instance here, show IP routers, showing all the connected routers, and this has come from OSPF configuration from that diagram, BGP configuration from the BGP diagram, and then C for the directly connected networks, which would then all come from the for the physical diagram. And one of the other nice things is that when we're doing it with overlay graphs, we could easily iterate over the nodes and edges to do things that are pretty mundane, such as IP addressing. If you're doing that with Python iteration, you just iterate over the subnets and then chuck an IP address on each end, which becomes quite easy to do IP addressing. The problem is, though, that if we can configure big networks, emulate big networks, running this command is the next thing that we should automate. It gets quite tedious to type that in on every device. So we've built extending the expect scripting. AutoNetkit can send it off to a collection client. We're using RabbitMQ, or we could use HTTP post just to say, these are the devices I want to measure. This is a command I want to run, such as traceroute or show IP route, to a collection client. It will run that on each of the hosts and send the results back. The problem is, though, if we just get the result back from expect, it's just going to be a whole heap of text, which is okay to look at, but again, not particularly nice to work with in a programming sense. So there's a nice library, TextFSM, which is working with semi-structured text. This came from Google Sydney network operations team. This is Python open source library. And the idea is that a lot of the network data that you get back has generally got structure, but it can vary a bit. So traceroute's fairly simple. You're just going to have the hop number, the IP address, and the delay here. When you get to things like show interface or the equivalents ifconfig in Linux, you're going to get things that could vary depending on whether it's running IPv4 or IPv6. So handling all these different type of conditionals, TextFSM was really nice to deal with any sort of structured text. So that could come with if you're working with a hardware device and getting results back from there. It's not necessarily just network, and that can then process it back. So the idea is that you've got your input, the template looks something like this, where it can handle the different cases, and then running that through TextFSM, you're going to get the output as just a series of lists. So here we've got the destination, the hop, there's no MPLS thing set, and then the delay. And so what we can do is that allows us to do some really powerful test-driven network programming. So if we go right back to Network X, as well as letting us deal with graphs, it's got a really powerful set of algorithms built into it, such as the classic Dijkstra shortest path. So we could give Network X 2 nodes in our network, run it across with the standard shortest path, and it will tell us the shortest path. And we could then take the output from TextFSM if we ran traceroute, and because we know the IP addresses that we've allocated in the network, we could easily build a reverse DNS kind of mapping to take this output back here down the bottom, the heap of IP addresses, and convert that into a list just with a few more list comprehensions, just doing a reverse mapping. And then we could do some quite powerful things. So for instance, this is showing, we could do traceroute, which I'll get to in a second, and also, for instance, showing show IP route. So we could run this as a network starts up and to see the routes changing. I've got some videos on the AutoNetkit website. So there's a lot of really powerful things we can do by stringing all these bits together. And just very quickly, this is a sped up video of showing the whole process. So drawing the network in YED, and then we can see the real-time visualization for each of the IBGP and OSPF diagrams, setting some attributes such as the autonomous system number. Now we have 3 ASs rather than just 1, so all those design rules are applied differently. We can use the API to set properties, and then this is just a compilation down to generate that resource database. The output configurations which are generated from there for each of those devices in the network, including the OSPF and BGP router configs, and then doing some analysis, so running shortest path directly, starting up the laboratory, which is just expect scripting to launch it. And this over here is, of course, D3 running, which makes all this fancy animation really quite easy to do. And grabbing the commands back and then doing the parsing of that with text FSM, sending that to the web browser as a path in JSON and viewing the result. And that's pretty much it. And those are the packages that are really good. Thank you.
Thanks, Simon. We still have a couple of minutes for questions. If anyone, a couple of hands went straight up there.
Hi, so first of all, mind blown. Awesome. And so if I understood correctly, you basically go from drawing a diagram to all the way to configuring routers.
Yeah.
And to me, this sounds like I could draw a diagram and configure a software-defined network like that.
Yeah.
If this were extended to, work with OpenFlow or something.
Yep.
Are there any plans to do that, or?
Yeah, I think in some way. So basically, I think we would stop at this point here. So rather than doing all the horrible expect scripting, a lot of the motivation from software-defined networking is better abstractions, which I think there's 2 parts in it. Bit philosophical. One of those is better programming abstractions, which we don't really have in networks. And the other thing is the mechanisms to push those out, and expect is pretty horrible. So the API is to push stuff onto a device, whether it's OpenFlow or Cisco's 1PK or whichever variant we have. I think that's important. But I think the other key thing, which I haven't seen a whole lot of in a lot of the controllers, is being able to describe your network at a high level and do operations to build what you want it to look like. And I think that's where something along the lines of what we've got with AutoNetkit could do that role. And getting from drawing and saying, I want this to connect to this based on this, and seeing the output, and then being able to compress that down or condense it down to having this kind of attribute. So I think we would go, in an SDN sense, we could use some of that, the early stages of AutoNetkit, and then have something like these attributes here, and then this could be, instead of BGP config, could be those OpenFlow parameters, and doing design rules from there, and using that sort of design API and this bit, and then pushing that out to a different package. So I think that's how it would tie in. Yeah, thanks.
Other questions? Not at the moment.
Have you looked at automated problem analysis of, detecting potential errors in the configuration?
Detecting?
Potential errors in the configuration.
Yeah. Again, it comes back to having the higher level of abstraction and doing some of those things. So one thing I did do, basic, was there's this whole thing about correct by design. So if you write your design rules right, it should be good, which is a bit of a cop-out. I think that you could write independently. Again, it's just basic graph stuff. You could then start to apply some design rules. So there'd be some on the lower level config gen, but I think there's also some design rules we could start to build, and this is something we have been looking at this sort of level here. So for instance, if you've got an OSPF graph, you shouldn't be connecting things in different areas to each other or different ASNs, or that you shouldn't be able to have disconnected things. So it's quite easy to apply a graph algorithm to look for disconnected components. You could do that, or you could check the attribute if, so in OSPF, everything should go through area 0 if it comes from different areas. That kind of thing you could easily do as a graph, looking at the components, looking at the connectivity between them. And so that way you could automatically, someone with deep network expertise could write those rules, and then anyone could come along and concoct these kind of design rules, verify them against that, and then get sane errors back at that level, as well as then being able to do some of the automated measurement right at the end as well to do some. So there's a few parts where some of that testing could come into it. And again, the DevOps people have a lot of that solved. It'd be nice to be able to do some of that in a networking sense. Or even the software engineering type of philosophy and methodology for testing and unit testing and things like that, you can start to get towards which again I think is some of the appeal of software-defined networking. But I don't think we need to have OpenFlow to be able to get some of the benefits of working at better abstraction. And there's also a whole heap of stuff on the internet now that people aren't going to replace overnight, that we can do a better job with what we've got now and then perhaps replace it in the future.
Any other questions? Thanks heaps for that, Simon. We have coffee beans and a coffee mug, thanks to Ritual Coffee and the PyCon organisers for you. And yeah, that was great.